Welcome back. Our next speaker is Gergely Berczi from Aarhus.
Thank you very much. Thanks for putting together this one-day workshop. So, as you see, or maybe you don't even notice, but I changed the title slightly. So it's a completely different thing I'm talking now, which I plan to do. But I talk about Hilbert scheme of points of singularities, hypersurface singularities. So the plan is that it's better this way, right? So
could you just speak a little louder?
I will try. Yeah. So we talk about hypersurface singularities, and in particular, if you take a plane curve singularity fxy equals 0, then there is a corresponding link, which I know by curly L, which is just the intersection of this the free sphere sufficiently small of sufficiently small radius, and so that's a link which is not a knot but kind of might have more than one component, but it's a link, and kind of a meta problem is classify topological types of singularities, and which could one way to do is kind of some sort of finding link invariants, and there's a long history of this in geometry, so that we know a lot of link invariants, Alexander, Humphrey, and so on. And kind of the principle is that somehow the geometric principle is that these link invariants should be and must be somehow must depend somehow through the geometry of the Hilbert scheme of points on the singularity itself. So this is a general principle which has several incarnations, and I will just present one of these. So that's interesting. For this, let me define what is Hilbert scheme of singularities. So you have a Hilbert scheme of k points on this plane curve singularity f. This is basically just the set of points on the Hilbert scheme on C2, the ambient C2, which sit in this curve. Or in other words, those ideals supported at the origin, so that f sits in the ideal. So that's the link. That's the singularity, Hilbert scheme of the singularity, and we can introduce different gradings on this, or nestings if you want. So one common nesting on this Hilbert scheme, if you just take two parameters k and m, and you take pairs of subschemes satisfying some conditions. The exact form of this is not important now. I just really wanted to formulate this conjecture, which was like a relatively famous conjecture from the last 15 years, and a motivating example. So this basically connects the some link invariant. This is the Poincare polynomial of the some sort of triple graded homology theory of the link, and the geometry of the Hilbert scheme of this, or at least refined Hilbert scheme of the singularity. So the principle here is that on the right hand side we see some sort of generating function of this omega stands for the weight polynomial. So something which you derive from the Hilbert scheme of the points of the singularity, and that's actually, you know, this one cooks out some sort of link invariant of the singularity. And there is some this conjecture in particular. Some special cases are already proved. So the Alexander polynomial is a special case, and then Maulik proved the t equals -1 case, which is the Humphrey.
What is omega of the?
That's the weight polynomial. Weight polynomial of this singular variety. So, but you know, if you just take the Humphrey polynomial, that's a special case of this triple graded one, and in that case you just substitute the Euler characteristic into your omega. There are some special cases, specializations of this, which we already know. So this is just, really just to present as a general principle that somehow what we expect and happens very often is that somehow some sort of geometry, in this case the Hilbert scheme of points on the singularity, encode you some invariants. A topology is the type of the singularity. So topology is the type of the singularity, and there's a direct way to encode this. Another incarnation of this is the main topic of this talk. Here the motivation is that the Hilbert scheme of points on the singularity also encode the so-called Iguda zeta function. So that's I've tried to explain in a very elementary way. So this is really a kind of a very elementary introduction into this. So we take a prime and then we write, for any rational number, we can write this rational number uniquely as some power of p, and times some rational number where a and b is not divisible by p. And in this case, the order and the norm can be defined to be m, and the norm is to be 1 over p to the m. This is a p-adic norm. And the field of p-adic numbers, or QP, is really the completion of this norm topological space. But, down like a simple, at least for me, like as a working mathematician, this means that the elements of QP are just Lorentz series in P, with coefficients in the field Fp, and this is actually a local field. So we take the p-adic, the ring of p-adic integers, which is the set of those elements of this where the norm is less than or equal than 1. In other words, we just take the Taylor series in P, and so this is actually a local ring, a compact local ring with a residue field equal to Fp. So there's a unique maximum ideal consisting of series with a zero constant. So A1 equals 0. So so the point here is that we can then define a measure on QP, and so can we normalize that the measure of the p-adic integers is 1, and that's actually nice, because if this is really a measure, then it's additive, so you can use this as the motivic basis of motivic or p-adic integration. Is that we can easily find nice measurable subsets with just by using pavings. So if you have a paving with isomorphic pieces, then you can easily find the measure of that piece. So and then we can. This is really an integrator. So you can integrate now, and for integration, it really just means technically that the change of variables rule actually holds. So. So this is kind of the elements of these p-adic integrals, and I would like to show you a very short, very simple example. So, more generally, we can also work with the finite extensions of this p-adic field, and in that case, we can take the ring of integers, which is the integral closure of Zp, and it's again a local ring with residue field equal to Fq, where Q is some power of p. So here's an example how to perform such an integration. So let's take, we want to integrate over Zp this function x squared norm to the s. So this is the p-adic norm. So so how would you do this? Actually, identify the level sets. So the level set for 1 is just where this norm is equal to 1, and it just means that z is this polynomial in p, which with a non-zero constant term. And in general, the level set Vm consists of those axes where is sitting the mth power of the maximal ideal, but not in the m plus 1 power of the maximal ideal. And it's everything is so easy. So now we can actually really just compute the measure of these level sets is this expression here, because everything is additive. And so how you integrate something is just basically you take the level sets. Once you know the measure of the level sets, you just add those up. And that's why you get this formula. So what this tells you actually that if you take such an integral, it's going to be a rational function in P or in Q in general. And but it's not just a rational function in P or Q, but it's a rational function in P to the S in this case. So S is this parameter here, which can be any rational, let's say integer right now. What can be anything basically. So you can do the same calculation, and you believe that it works for any monomial function. The problem is that if you the problem is that what is the real challenge if you replace this polynomial with another polynomial, and you know we would like to do this for some plane curve singularity in the end of the day. It becomes really complicated because the level sets are less handy. And so the solution here is sort of if you have such a function, for instance, then you can take some resolution of that. So this f, and use the integral. The integral formula means that you can actually pull back integration to the blow up, and you can also pull back the function itself, and locally at the exception divisors is going to be monomial. So any function is going to be monomial. So you can use this trick which you already seen before, this one, for close to the exception divisors, and put together the final formula using the exception divisors. That's kind of the DANF trick. And so let me introduce this terminology before I just go on. So the zeta function, this is this over, now this, let's say this is just the Igusa zeta function, is going to be, depends on a function f, now in d variables, so not necessarily a plane curve, but a hypersurface singularity, and s is the integral over the d power of the integers of f known to the s. So this is an important function. Another quantity which I introduce is really the number of those points which are in this set where you have you only care of the jet of this element of this periodic field. So we quotient out by the m power of the maximal ideal. So these elements here are represented by a polynomial of degree m. So that f vanishes on this modulo the m power of the maximal ideal. So this is actually this is what denoted by nm, and the Poincare series of f is now given as a generating function for these numbers. So the point is that this is a classical theorem of Igusa, which says that this Igusa zeta function, so this integral, is a rational function of q to the s, and it has this direct expression through q. The proof is really simple in the sense that, so the idea is that you really define again these level sets Vm. So those are the level sets for this integral. So those elements in x in OK to dd, where the norm is less than or equal to 1 over q to the m. So and there's a direct connection between nm and this Vm due to this additivity of the measure. But of course the main object here is this, and the main conjecture, one of the main conjectures in regarding these Igusa functions is the monodromy conjecture. So it says that if you have a this s is not a pole. So let's have a, so what it says that if you have a pole of this Igusa zeta function, then e to the 2 pi I times that pole, s is double used here, I'm sorry. So this s is not the same as this s. So the e to the 2 pi I, the pole is an eigenvalue of the monodromy action on some minor fiber at some point. And so somehow that's kind of the main conjecture here, and so technically what you can do, and this is actually known for plane curve singularities, and how the proof of DANF and Löser actually works is roughly speaking is we take this Igusa zeta function. As I mentioned before, it's not easy to calculate these level sets for generic f, but if you have a resolution, then you can handle it using through the exception divisors. But the problem is that when you actually use a resolution, the resolution is not unique, of course. But whenever you have a resolution, you can make a calculation, so you get some sort of rational expression and you get some poles. But some of those poles become fake poles, which means that some of these poles will actually cancel out with some other poles, and they will not survive in the end. And of course, this is what we expect because the resolution is not unique. So this is what must happen. This. So it's really hard to actually work out what of these actually become the real poles. So if there would be if you had a better way or a direct way to calculate this Iguza integration or Iguza zeta function, that would be great. So for this reason. So and here is like maybe some first baby steps toward this direction. So let's focus on just curving their Hilbert schemes first. So what is this? So we take, we recall that what is, I don't have to recall. So Hilbert KF is just the Hilbert scheme of F. And this curvilinear Hilbert scheme C Hilbert KF is a set of those Hilbert scheme on CD, so the ambient space, such that first of all F sits in the ideal, and it has the algebra. It has this fixed type, which is a Morin type. So this is Ct over T to the K. In other words, this is the intersection of the Hilbert curvilinear schemes on CD and the Hilbert scheme of points on F. This is usually, it's, you know, on CD this is like it's a irreducible component, but for a generic F this is not even irreducible. We don't, you know, the components are not equal dimensional and so on. So it's kind of a
so you close it, right?
We don't here. We don't close it.
Oh, okay.
I really want to take regular jets. Yeah, there's some inconsistency with the notations. Yeah. So the Tasker model for these curvilinear Hilbert schemes on CD is really says that if you have this is just says that curvilinear Hilbert schemes are the ones subschemes which are contained in a smooth jet. So in other words, a point here can be described as a k-1 jet from C to CD quotient by the reparameterization group of C. So it's not sometimes a non-reductive quotient. But, and here's this actually the really nice correspondence between these two things. I think it's a super nice observation. So this, you see, the curvilinear Hilbert scheme is really is a set of D polynomials of degree k, such that F vanishes on that modulo T to the K. This is what I told you. And here's the next line. Let's do this the same with now the p-adic field, on the p-adic field. So what is this? We take the elements in the p-adic integers. So, but these are regular elements. I mean that in mk modulo mk to the k. So and you know, so I want to say is that it's not just mk over mk to the k, but we take the regular part. So this the linear part of these polynomials are non-zero. So let's go back to what these are. So this p1 is going to be a p-adic integer. So it's going to be a polynomial in p modulo mk to the k, but it's just a polynomial of degree k with coefficients in zp. I would like the linear coefficient to be non-zero. That's why they call the regular. Such that if I feed these in F, I get 0 modulo, not T to the K, this is a misprint, but modulo MK to the K, I'm sorry, M to the K, I'm sorry, MK to the K. So this is a misprint here. So you see that these two are very, you know, kind of identical. Here we take complex polynomials of degree K. Here I take p-adic integers of not modulo the K5 of the maximal ideal. So, and you know, the connection is really clear. So this previously I noted by nk, that number is equal to the f number of points over fk of the Hilbert scheme of points times diff k. And so actually this leads to this nice theorem of Berzinelli. It's from last year, is that you can form a generating function of the number of points of the Hilbert scheme over fq. That's actually the curvilinear Hilbert scheme of f. And that is that encodes really equals a zeta function It's an equals zeta function. It's a partial, the regular. It's not on the full domain, so it's not the full equals zeta function, but the domain is restricted to the regular part. And so somehow the hope, and I finish here, is that so the principle is the following. So we have the curve in the Hilbert scheme. There is this equals integrals of the regular domain, and the monodromic conjecture. So the question is, using this formula, and what we work now is kind of a generalization of this for not just on the curve inner locus, but in general. So can we, if you can put our hands on the full domain here and write the full equals function as some sort of generating function of counts of the Hilbert scheme of points, then there might be a hope that actually using this model, this is the task curve model, to get explicit or direct formulae for the equals functions using this. And then that's actually it, because I think I just say thank you for attention.
The questions.
Is it a perfect correspondence, or it's a part of it? So the previous.
Yeah. So this is just there is a perfect correspondence between this regular domain and the curve inner Hilbert schemes, because this is really just this is actually these two lines here. So we talk about the curve inner Hilbert scheme is this. Of course, this is not precise here, so I really want to take polynomials with non-zero. One of the such that one of the PI's has non-zero linear term, and the same condition here, and that will correspond exactly to the curve inner Hilbert scheme. On the other hand, this will correspond exactly for this regular domain on the of the periodic regular periodic domain. But the question is, I think maybe if I understand it well. So the question is, how can you identify the rest of the domain? So if you have a generic point there is a way actually. So on plane curve, for plane curve singularities, the full domain corresponds to the so-called one generated part of the Hilbert scheme of points on F. So if you have a subscheme on C2, or you have an ideal in C2 which represents a point on the Hilbert scheme, F must be a generator because it's on F. And if you have another generator of this ideal, so it means that it's generated by two elements, then generically that gives you a point on the Hilbert scheme, and that's what we call this is what we call the one generated element part of the Hilbert scheme of points on F. And that's actually what corresponds to the full domain. So, but of course, for any other types, if you want, you can work out a similar formula. This is what we do actually. We fix the type of the Hilbert scheme, and then there's a corresponding domain on the left-hand side, which you can cover.
Any other questions? Let's thank the speaker.